You can buy a 3D printer today for the price of a decent pair of shoes, or the price of a luxury car. If you choose the wrong machine for your specific workflow, you waste capital and create severe operational bottlenecks. Many buyers look at the sticker price and completely ignore the total cost of ownership. They miss the hidden, manual labor hours required long after the print actually finishes. So we aren't going to look for the objective best printer. Instead, we are mapping 3 distinct technology pipelines to the exact business scenarios they were built to handle. Every 3D printing purchase requires you to balance 3 critical criteria on what we call the 3D Investment Scorecard. First is structural integrity. Do your parts need physical strength, isotropic properties, or exact dimensional tolerances? Next is visual realism. Do you need full color fidelity, varied material textures, or perfectly smooth surface finishes straight off the bed? Finally, total cost of ownership. This is the combined burden of the initial hardware cost, the ongoing consumable materials, and the manual post-processing labor. No single machine on the market scores perfectly across all 3 categories. The investment decision is entirely an exercise in choosing your preferred trade-offs. Let's start with FDM, or Fused Deposition Modeling. This runs on low-cost thermoplastic filaments like PLA or PEG, usually costing between $20 and $50 per kilogram. Because the material is cheap and the software allows you to build hollow internal grid structures, your structural prototypes cost pennies and print incredibly fast. But there are steep physical trade-offs. FDM parts have highly visible layer lines. They lack isotropic strength, meaning they snap easily along the vertical axis, and those tiny gaps mean they cannot hold water under pressure. On the flip side, the post-processing workflow is highly efficient. Parts print completely dry. You break away the supports by hand, and there are no chemical washes required. The friction hits when you need a smooth surface. Achieving a clean finish requires heavy manual sanding or scraping, which easily breaks delicate, intricate geometries. FDM is the ultimate tool for budget-conscious form and fit iteration, as long as you are willing to sacrifice surface finish and absolute structural density. Then we have SLA, or stereolithography. Instead of melting plastic, SLA uses UV-cured liquid resins. This bumps up your consumable costs, often passing $50 per kilogram. For that price, you get ultra-tight tolerances down to 25 thousandths of a millimeter. You get smooth, semi-matte finishes and fully dense, watertight parts. The material trade-off here is physical flexibility. Depending on the exact resin formulation you choose, SLA parts can be highly brittle. Then comes the post-processing friction. SLA mandates a dedicated cleaning station where every part is chemically washed in highly flammable isopropyl alcohol. After the wash, parts must undergo intense UV heat curing to reach their final mechanical strength or meet biocompatibility standards. You are introducing a messy, hazardous workflow into your space. It requires proper ventilation, safety protocols, and dedicated bench space that you simply cannot put on a standard office desk. SLA guarantees functional engineering precision and isotropy, but it forces you to adopt a high-friction, chemically intensive pipeline. Finally, there are full-color polyjet systems. These use voxel-level multi-channel materials and UV-curable inks. Both the initial hardware and the proprietary consumables demand a massive premium. You gain the ability to produce photorealistic, multi-material, presentation-ready models. We're talking up to 10 million distinct color variations in a single print. You can take a highly complex mechanical assembly and print it with exact voxel-level color precision to simulate what the final product will look like. Now, contrast polyjet with CJP, or color jet printing. CJP also produces full-color models, but it uses a powder bed and liquid binding agents, making it popular for rapid architectural layouts. The structural trade-off with powder-based CJP is severe. The resulting printed parts are highly porous and incredibly fragile. To combat this, you face a messy secondary infiltration process. These fragile parts often have to be dipped in superglue or epoxy just to achieve basic durability and lock in the color vibrancy. Full-color systems deliver an unparalleled aesthetic presentation, but they demand premium operating budgets and produce outputs that require delicate handling. The quality of your output technology must strictly match the fidelity of your input data. This is especially true in high-stakes reverse engineering. Take complex aerospace components, where dimensional tolerances mean the difference between successful launches and catastrophic failures, or bespoke precision parts required for specialized marine and aquatic engineering. When you capture data in these fields using advanced industrial CT scanners or coordinate measuring machines, you have to use SLA printing to reliably reproduce those exact dimensional validations. Investing heavily in premium scanning and reverse engineering data is entirely wasted if you attempt to print the final validations on budget structural technology. Let's map out the decision. What is your required outcome? If you need high-volume structural form and fit testing on a tight budget, invest in FDM. Just prepare for rough surface finishes. If you require exact dimensional validation for reverse engineering, invest in SLA and prepare for a hazardous chemical workflow. If the model is the final commercial product, choose full color systems. Expect extreme hardware costs and part fragility. Don't pay for 10 million colors to print a functional gear. And don't rely on extruded plastic to hold water.